In this one we've got a incline. It's got a little pulley up at the top. It's got a little bit of string attached to a mass. The incline's at this angle theta. We've got a spring with a spring constant of K. Now on this one, the mass is pulled up a certain distance d. So it's pulled up sort of to where it's at that point, and we'd have d. So at that point we've obviously increased the gravitational potential energy on this mass, and we've got some elastic potential energy. And then we let it go, and the whole mass is going to obviously pull back down. But it's not just pulling back down, we're getting some rotational motion taking place with the disc at the top here, or the pulley. And so there's going to be, by the time the spring comes back to being nice and unstretched, it's going to be a loss of, the mass is going to have a velocity, and the disc is going to have a velocity. So two velocities, rotational kinetic and just normal kinetic. Now, with this mass just sitting here normally, unstretched means the position it's at right now. Now obviously a mass in this position has compressed the spring a little bit. But we don't have to worry about it. We're talking unstretched in the situation we've got right now. So this is one of those energy ones, and they come up a lot in this type of calculus type situation, where we've got to work out what's actually going on. And what we actually end up doing is just equating the energies, of course. Now we've got the energy that it's that you've increased by pushing it up, and that's not just mg, it's mg sine theta, because it's the vertical rise that's important. So mg sine theta is energy gained, but we've also got some elastic potential, which is half kd squared. Now that all gets converted into two types of energy, 1/2 mv squared plus 1/2 I omega squared. So that's the energy equation. If we write all this out, we've got the 1/2 m omega squared r squared. Where'd that come from? That's half mv squared, plus 1/2 I omega squared equals mg sine theta, plus 1/2 kd squared. Looking good. Can we do anything obvious at this stage, like cancelling out m's? Not really. We've got an m there, we've got an m there, we've got m's in there which we could bring out because we know the rotational inertia of a disk, but it's not going to help us because k's there. Although in saying that, I think it does. I think we could come out with a slightly easier formula, because k is equal to m omega squared, right? So I think I could do this. I could get them all out of there. But we won't do that. What we'll do is we'll keep it nice and straightforward, and we'll bring out the omega squareds first. The omega squareds here, and that gives us 1/2 mr squared. I keep changing. Do I change from big r's to little r's? I seem to do that quite a lot. Anyway, we'll keep it just little r's there. And we've taken, so that just comes out plus 1/2 I equals mg sine theta plus 1/2 kd squared. So obviously we can just bring that through there. We're already down to getting an omega squared, which is nice. So we've got the 1/2 mr squared plus 1/2 I. And looking at that, I think if we multiply the top and the bottom by 2, we're cool, aren't we? Because we can get rid of these halves. So we'd end up with the 2 there, that half is gone, that half is gone, that half is gone, and then all we need to do is put a big square root sign on it and get rid of that one. So omega equals the square root of 2mg sine theta plus kd squared all over m r squared plus I. And we're done.